next is practical aspect of FDM. So practically there are number of modulation and demodulation happens. It is not like that if we directly modulate the carrier and we transmit the signal. In case of FDM, we perform modulation in multiple stages. So suppose we have a message signal which is our speech signal in case of a frequency division multiplexing, because we are going to use filter method. So the range of this particular speech signal is actually, we write 300 hertz to 3400 hertz, but practically it is considered as 0 to 4 kilohertz. Now we in practical FDM we consider 12 message signals together, 12 message signals. So for 12 message signals we assign carrier frequency by formula 60 plus 40n. This is in kilohertz, where n is number of user and it is varying from 1 to 12, because in starting we will be having 12 users, 12 persons are there, and for that 12 person we will assign the carrier frequency with the formula 60 plus 4n. For first user n equal to 1, for second user n equal to 2, and for 12th user n will be 12. Now we will perform the modulation, and because the speech signal is having the range 0 to 4, so let us consider the spectrum from 0 to 4 like this. This is 0, this is 4, this is in kilohertz, and the mirror image will also be there up to -4. This is, I am talking about the first user. So if we are having the first user, then what will be the carrier frequency for that user? So that will be 64. So it means that it is multiplied with the carrier which is cos 2 pi f1t, where f1 equal to 64 kilohertz from that formula. So we will be having a double sideband signal. This will be shifted to 64, 0 will be shifted to 64, and we will get the double sideband signal like this, 68 and 60. This is a double sideband signal in which this is upper sideband and we are having lower sideband. But because in FDM we consider single sideband modulation, and to generate SSB signal we use filter method, and after generating the double sideband suppressed carrier we suppress one of the sideband. So let us say we are suppressing this upper sideband and transmitting this lower sideband. So for SSB-SC modulation using filter method, SSB-SC we are generating which is ranging from 60 to 64, because we are considering lower sideband. Lower SSB modulation is happened in filter method or FDM. So now the first user will be having the range 60 to 64. Similarly, we will be having second user, and what will be the range of that second user? So if you consider, suppose second user, suppose because the range of all the user is same, so this is also having -4 to 4, but the shape is different. Now we are having another frequency for second user, n will be 2, so that is 68. So if it is 68, then the double sideband will be generated, and this double sideband will be like this. This is 68, this is 72, this is 64, this is lower sideband, this is upper sideband. So first we generate double sideband suppressed carrier, and then we consider lower sideband and suppress upper sideband. That means we will get 64 to 68. So this SSB-SC signal, which is for the second user, will be ranging from 64 to 68. That means here, somewhere here. So first user is having the range 60 to 64, second user will be having the range 64 to 68, similarly third user will have some range. So the overall range of the 12 channels, combined range of these 12 channels, because we have total 12 users. So and in FDM we combine all the signals, so we combine all the 12 users frequency spectrum, then the range is from which frequency range that we have to calculate here, 4, 3, 2 and 1. There are 12 users. So first user was having range 60 to 64 kilohertz, second user was having the range 64 to 68, third user will be 68 to 72, 72 to 76, 80 to 84, 84 to 88, 88 to 92, 92 to 96, and then this is 100 and 104 and 108 kilohertz. So when we combine all the 12 user spectrum, we will get the range from 60 kilohertz to 108 kilohertz, and this is called basic group. This is called basic group. When we combine the 12 users, then this is called basic group. And now this basic group is having the range 60 to 108 kilohertz, and all are having carrier frequency. So here we can calculate this carrier frequency, that is from that formula, and it is 64 for second user. This carrier frequency is 68, for third user 72, then 76, then 80, 84 and so on, 88, 92, 96, 100, 104 and 108. This is the carrier frequency. Now this basic group is again combined in the form of super group. We consider the 5 basic group, because here we consider the 12 message signals. Now after considering this 12 message signals, we are getting a basic group, and this basic group is actually considered as a single message signal, and we will perform the modulation again. So this is the first stage of modulation, in which the carrier frequency is used as 60 plus 4n. Now we will use the second stage of modulation. It means modulation is happening in multiple stages. First stage is to generate basic group, and for that the carrier frequency is 60 plus 4n. Now we will be having a super group, that is the combination of 5 basic group. So now we have a basic group which is ranging from 60 kilohertz to 108 kilohertz, and this basic group is modulated with carrier frequency 372 plus 48n kilohertz, and here the n is 1 to 5, because now I am going to consider only 5 basic group. So what will be the range of this 5 basic group? Range of this 5 basic group, which is known as actually a super group. Now we will call it as super group. The combination of 5 basic group is called super group, and after super group we have master group and so on. So the modulation is happening in multiple stages, but we have to remember only up to the super group. There may be more values, super group, master group and so on, but we do not need to require up to that value. The question may be asked and up to this group only, that is super group. So what is the range of this super group in FDM? It can be asked, and if it is asked, then you have to calculate with the help of this particular carrier frequency and this as message signal. So let us calculate it. If we have the basic group ranging from 60 to 108, suppose this is 60 to 108, 60 to 108. This is our message signal now. And now we are modulating the carrier FC for the first user. For the first user n is 1, so if I take n equal to 1, then this is 420. This is 420 kilohertz for first user. When we put n equal to 1, 372 plus 48. 372 plus 48 is 420. Now what will be the range? So the range is actually it will shift to 0 will be shifted to 420 and this will be the upper sideband and this will be the lower sideband. Because if this is the range 60 to 108, so there will be a mirror image from minus 60 to minus 108, and now when this modulates this carrier, then this spectrum will shift to 420 and minus 420. So we required only the positive frequency, so we draw here only positive frequency, and the 0 is shifted to 420. So this is 420 plus 60, which is 480, and 420 plus this 528, 420 plus 108, this is 528. So 520 and now 420 minus 60 is 360 and 420 minus 108. So if I subtract this, we get 312. So this is the lower sideband, this is the upper sideband. We consider only lower sideband, lower single sideband. So lower single sideband we are considering, we will select this and reject this one. So the first will be having the range 312 to 360. So that is the gap of 48. Here this is 60 plus 4n. So 60 plus 4n, so the gap between the two spectrum is 4, 60 to 64 and 64 to 68. Similarly, here we are getting the gap which is nothing but the bandwidth of this. Here we are getting the bandwidth of this particular band pass is 48. So here also we are getting 48. So now to get the next range, we will add 48. So if I add 48 into 360, so 360 plus 40 is 400 and 408. Now 408 plus 48, we get 456, and 456 plus 48, 456 plus 48, 504, and 504 plus 48, 552. So the range of this supergroup is from 312 to 552 kilohertz, and this is having carrier frequency, 420. This is the carrier frequency to the supergroup, 420 kilohertz, and after adding 48 means n equal to 2, so that is 96, 372 plus 96, we get 468. So 468, and then adding 48 again, we get 516, and similarly you can calculate for 4 and 5. When you put n equal to 4, n equal to 5, you will get this carrier frequency. So this is the range of supergroup. If it is asked to you, then what is the range of supergroup in FDM, then you can say 312 to 552 kilohertz, and if it is asked that what is the range of basic group, then it is 60 to 108 kilohertz. So this is the practical aspect of FDM. Practically the modulation happens in multiple stages, and that multiple stages, when we combine the 12 signals, we get the basic group, and to generate this basic group, we consider the carrier frequency as 60 plus 4n, and from that basic group 60 to 108 kilohertz, that is considered as a single message signal, and that basic group forms supergroup, which is the combination of 5 basic group, and to generate the supergroup we consider the carrier frequency 372 plus 48n, and we get the range of supergroup. And similarly practically, and after this supergroup we generate the master group and more groups are considered. But up to this point we can remember, or we can learn this, or we can derive these formulas, and that is sufficient for other PSU exams. So next is workbook question, that is based on frequency division multiplexing. Question number 48, 10 real bandpass message signals, each of bandwidth 3 kHz, are to be frequency division multiplexed on a bandpass channel with bandwidth B. If the guard band between any two adjacent signals should be 500 Hz and there is no need to provide any guard band at the edge of bandpass channel, the bandwidth B should be at least. So the signal is already converted into a bandpass signal, so we don't require any further modulation, and that bandpass signals are frequency division multiplexed, that means they are combined now. So suppose we have first message signal, this is the first message signal, and this message signal is having bandwidth 3 kHz, so it is given that this is having bandwidth 3 kHz. And similarly we have ten message signals and we are combining it, that means we are having the spectrum like this. Suppose this is 3 kHz, this is again 3 kHz, and so on up to this is 3 kHz after combining. Combined signal or FDM signal. This is one message signal. So we have one message signal and having bandwidth bandpass signal. This is the bandpass signal, so this has been already shifted to some frequency. So whatever will be the carrier frequency for the first message signal, it is shifted to that particular frequency, and the bandwidth is coming to be 3 kHz, and that bandwidth is same for all the 10 message signals. So we have first message signal, we have second message signal, and this is the 10th message signal, and all are having 3 kHz bandwidth. This is also 3K, this bandwidth is also 3K, and this bandwidth is also 3K. For all this is 3. And the guard band, there is no need to provide the guard band at the edge. So here we don't need to require a guard band, and here also we don't need to put guard band. This is the guard band that we required, and here at the edges we don't require the guard band. So this guard band is having 500 Hz, this is 500 Hz. So between two adjacent spectrum there is a guard band of 500 Hz. Now what is the bandwidth of the channel? If we want to transmit this combined signal, then what should be the bandwidth? So this overall bandpass signal should have bandwidth ranging from highest frequency to lowest frequency. So this will be the bandwidth of FDM. Now how do we calculate bandwidth in case of FDM? Because all the message signals are having same frequency or same bandwidth, so bandwidth of FDM is n times bandwidth of message signal plus n minus 1 times guard band. So we have 10 users and each are having 3 kHz bandwidth, and 10 minus 1 into guard band, that is 0.5, all are in kilohertz. So here we get 30, here we get 9 into 0.5 kilohertz, that is 9 into 5, 0.5, 4.5. So we are getting 34.5 kilohertz. So this is the bandwidth of this channel or FDM signal, and this bandwidth is 3, 3, 3 and so on up to 10 times, and because of two adjacent component we have one guard band. So out of for 10 users we will be having 9 guard band. So from this formula also we can calculate, and the result is 34.5, and according to the option, the correct option is option B. Now coming to the next question. Question number 49. Assertion and reason question है. The basic group in an FDM system occupies a band 60 kHz to 108 kHz in frequency. So we know that the basic group in FDM occupies this range, so this is correct. The reason is the voice channel in FDM are band limited to 4 kHz. So yes, the voice channel is band limited to 4 kHz because we took the 0 to 4 kHz, and the carrier frequency FC is 60 plus 4 n kHz and are 12 channels in the basic group. So because of the 12 channels we considered, and in basic group, and the carrier frequency was 60 plus 4n, that's why we were getting the range of basic group from 60 to 108. So the reason is correct for that assertion. So the both the statements are true, and the R is correct statement, correct reason for A. So according to the option, that is option A. So for question number 49, the correct answer is option A, because both the statements are correct, because basic group we generate, and that is having the range 60 to 108. And why it is having the range 60 to 108? Because we considered the message signal ranging from 0 to 4, and 12 such channels are considered, and after considering the 12 such channels with carrier frequency 60 plus 4n, we got the range 60 to 108. So the correct answer is option A. The last question for this particular chapter is, in a carrier telephone system, a basic group occupies a frequency band of. So just we discussed the basic group is ranging from 60 to 108, and according to this, the correct answer is option B. So this is your first chapter, that is amplitude modulation. So these are the number of topics, and there are number of questions we solved, that is total 50 questions we have solved. There are practice questions given to you, assignment questions given to you. You can solve these questions now, and I hope this question is now no longer tough for you. We have discussed all the concept in very detail, and which is required for the GATE exam. There may be more practical aspects, but for the GATE exam, this particular chapter we have discussed in sufficient detail with sufficient numericals. So now you can directly move to the practice and assignment questions, and then you can solve the questions from different test series. So our next topic is vestigial sideband. So we know from the type of amplitude modulation there are 3 types: double sideband suppressed carrier, single sideband suppressed carrier, and vestigial sideband suppressed carrier. The advantage of this vestigial sideband is in the TV transmission. So in TV transmission, the video signals are having low frequency range, in which there are number of information. There is a good information lies in the low frequency range, and that's why we don't consider the double sideband suppressed carrier or single sideband suppressed carrier, because in single sideband suppressed carrier the lower sideband is completely eliminated, but the video signal is having low frequency response. So that's why we have to consider some portion of lower sideband, and one sideband is completely transmitted in case of vestigial sideband. So the application of this vestigial sideband is in TV transmission. Now we have seen the bandwidth requirement of vestigial sideband, that is more than the single sideband but less than the double sideband. So it is actually a compromise between the double sideband and a single sideband. Now we will see here the generation and detection of this vestigial sideband with the help of vestigial sideband filter, that is also known as sideband filter. So the generation part is, or the transmitter, we will generate double sideband suppress carrier first with the help of balanced modulator. And here we will be having a VSB filter or sideband filter. Let us say this is H I of F. In balanced modulator we should have a carrier signal AC cos omega CT, and at the input of balanced modulator other is message signal. So here we get a vestigial sideband signal. This is the VSB signal, and this is X of F, this is suppose Y of F. This is the transmitter. Now the receiver part is, simultaneously we are drawing the receiver part. The signal is received with the help of synchronous detector only, and the synchronous detector is balanced modulator followed by the low pass filter. Here the carrier should be synchronized with the transmitter carrier frequency. So omega CT, here we are getting Y of F because vestigial sideband signal should be the input. This is Z of F and this is S of F, suppose. So here we will discuss the output of each block, and let's find in which condition we can get the message signal back. So X of F, what will be the X of F? If the Fourier transform of this MT is M of F, then M of T multiplied with cos omega CT, we get X of F equal to 1 by 2 M of F minus Fc plus M of F plus Fc. This is the output of balanced modulator, which is a double sideband suppressed carrier signal. Now it is passing through the sideband filter. The sideband filter is having response Hi of F, suppose. So Hi of F, so whenever we pass it through the any system, the frequency domain, in the frequency domain they gets multiplied. So the output Y of F will be X of F multiplied with Hi of F. These two will be multiplied. In time domain they get convolved, and in frequency domain they get multiplied. So whatever will be the X of F, it will be multiplied with HIF. So after this we get this H of Y of F, which is output of transmitter, which is vestigial sideband signal. Now this Y of F is input to the balanced modulator, where we have locally generated carrier AC cos omega CT. So if I consider, suppose AC is 1, so let's remove it. So it will be easier to represent, that's why I am taking it as 1. It is you can consider it also, there will be no problem at all. Now Y of F modulates this carrier or multiply, so this Z of F, output of balanced modulator at the receiver, will be again 1 by 2 in bracket Y of F minus Fc plus Y of F plus Fc. Now we have Y of F, so from here we get 1 by 2 Y of F minus Fc, that means X of F minus Fc into Hi of F minus Fc plus X of F plus Fc and Hi of F plus Fc. Now we also know the value of X of F, so X of F minus Fc we can calculate using this expression. So what will be the value of Z of F? This Z of F is X of F minus Fc, 1 by 2, so this is 1 by 4 now, we have x of f and we have to calculate x of f minus fc. So when I substitute f by f minus fc, we get x of f minus fc. So this is m of f minus 2fc plus m of f minus fc plus fc multiplied with this whole term is multiplied with HIF minus FC. We are talking about this term, so HIF minus FC plus x of f plus fc we can get. So x of f plus fc will be m of f plus fc minus fc. I replace f by f plus fc. So if I replace f by f plus fc, then we get x of f plus fc. So here f is replaced by f plus fc. So this fc should get cancelled, and in the second term it should be added. So plus of f plus 2fc, and this term is multiplied with hi of f plus fc, bracket close. Now we have 1 by 4 in bracket m of f minus 2fc plus m of f, this whole term is multiplied with hi of f minus fc plus m of f, this will be cancelled. So m of f and m of f plus 2fc, and this whole term is multiplied with hi of f plus fc. Now this is f minus fc, means it is shifted to 2fc, it will also be shifted to 2fc. This z of f will pass through, low pass filter, so it allows only low frequency signal and it will suppress the high frequency signal. So 2fc is a high frequency signal, so it will be suppressed. So the output of this low pass filter S of f would be the high frequency signal will be suppressed. So this will be suppressed, and we get only output of this low pass filter, which is 1 by 4 m of f, common in both the term, we get hi of f minus fc plus hi of f plus fc. We will get these two terms. From here m of f, hi of f minus fc, from here we have m of f multiplied with hi of f plus fc, m of f is common, so we get hi of f minus fc and hi of f plus fc. So this is not the message signal which we want to recover properly, because there is some extra term, this term is extra. So here at the output of this low pass filter we can substitute an equalizer, and the characteristics of this equalizer should be, or you can also say that this low pass filter should have characteristics like H equalizer of f is 1 upon hi of f minus fc plus hi of f plus fc. If you will consider the characteristics of the filter at the output of this low pass filter in this way, then this term will be multiplied with this term, because it will pass through another equalizer and the response gets multiplied, and this response after multiplication we get only the message signal, because when you multiply these two terms, this output will be S naught of f, suppose 1 by 4 m of f, after multiplication you will get 1 by 4 m of f, because this he of f will be multiplied with this. So you can also write like S naught of f equal to S of f multiplied with He of f. So when these two signals will multiply, you will get the pure message signal. So you have to keep the characteristics of the filter in such a way that Hi of f and Hi of f minus Fc and Hi of f plus Fc should be constant. There can be two consideration. If one way is to put the equalizer at the output of low pass filter, and if you consider equalizer at the output of low pass filter which is having this characteristics, after multiplication you will get the message signal back. Or if the value of this is constant, if the value of this is constant, then we will get 1 by 4 m of f and some constant value. So that will affect only our message signal amplitude, not its frequency range. So if this is constant, then also we can get the message signal properly. So in this way we can consider the vestigial sideband analysis, the transmitter and the receiver part, and message signal can be recovered with the help of this synchronous detector if you properly select this particular sideband filter. This sideband filter should be selected in such a way that if I shift the characteristics or the response of this sideband filter to Fc and minus Fc, then it should be a constant value. If it happens, if the characteristics of this filter is considered in such a way that after plotting this particular expression we get the constant value, then this term will be constant automatically and we get 1 by 4 m of f. Or you can also say if it is not constant, then you have to keep an equalizer circuit which should give the inverse response of this particular response of filter. So if we get this response, this will be cancelled out and we get our message signal. So there may be two ways, any condition can be given to you, maybe in case of vestigial sideband what will be the condition if it is asked, then you will consider this condition, or if it is asked that what is the characteristics of equalizer in vestigial sideband, then this is the condition, but inverse of this particular condition will be the characteristics of equalizer. So ultimately this particular condition is important, Hi of f minus Fc and Hi of f plus Fc. Either you have to take it constant or you have to take the inverse of this as characteristics of equalizer. So this is the vestigial sideband.